Hello everyone. The title of this video is Finding Input and Output Values of a Function. Now each example I'm going to be doing in this video is taken directly from a free online textbook at openstax.org. I'm in their Algebra and Trigonometry text, section 3.1 called Functions and Function Notation. And I'm under the heading Finding Input and Output Values of a Function. Alright, so let's just get started in the examples here. I have them written out. Alright, so yeah, we're just given a function, an equation, a formula for a function, and asked to find, certain inputs or certain outputs. Alright, so we have to understand something about what's called function notation. Do this off to the side here. Function notation. Alright, so so say if a quantity A is a function of another quantity B. Now I talked about what this meant in a previous video on determining if relations represented functions. Remember, when I say that A is a function of B, that means that each value of B is paired with or corresponds to exactly one value of A, right? Or each allowable value of B corresponds with exactly one value of A. Well, if A is a function of B, then we can write the following. We can say that B is equal to a function of A. So let's say like f of A. Pardon me. B equals f of A. This is called function notation right here. This is said f of A, right, if you were saying it out loud, a function f of A. The part of this before the parentheses, f there, that's the name of the function. So you don't have to call it f, you can call it really whatever you want. Give it a name, say what it does. Right? But usually it's just going to be a single letter in our books here, our text. So we have the name of the function, then the variable or variables. I mean, you can have functions of multiple variables. Now, in this algebra and trigonometry text, we're gonna be only looking really at functions of one variable. You have the input variable, right, inside the parentheses, and then the entire thing, right, this f of A represents the output B, right? See how it's equal to B, right? So it represents the output B, this entire thing called f of A. Alright, so up here I'll point out all this same stuff in example 1. Oh yeah, and I'm sorry, the examples are taken from the text, right? Like I said, they're taken either from the examples in the reading or the try it problems in the reading, or from the exercises at the end of the section from that OpenStax book that are related to this particular objective. I failed to mention that earlier, I apologize. Alright, so for example 1 here, got, g of m, right? We would say g of m. And I know you want to say g times m, right? People are tempted to do that. Just hopefully in the context of whatever problem you're reading, you'll understand if it's multiplication or function notation, right? With practice, you should get the idea. All right, so this, again, g is the name of the function. All right, that's the name of the function. This function's called g. That's being represented by this equation. The input variable, my input values are going to be this m. Right? And then g of m, right? The entire thing here, g of m represents the output, right? And then on the other side is also the output. It's just telling you how to calculate the output given an input of m. Right? So the expression on the other side should be an expression involving the input variable, and it just, how to calculate the output. So it also represents the output, but just shows you how to calculate it. And that's the way all these formulas with function notation will be set up. Right. So here we have this function called g, and it's, g of m equals the square root of m minus 4. So what this tells me is that I take an input m, I subtract 4 from it, then take the square root of that result, and I'll get the output called g of m. Right. And the ordered pairs in this function, remember a function is just a set of ordered pairs. The ordered pairs in this function g will look like the following. Right, look like this. You'd have, remember how ordered pairs go in relations and functions. You have your input, which is some value of m here, and then you have your output, which is called, g of m. Right, so input m, comma, output g of m. Or input m, and then, again, this other side, how the output is calculated, also represents the output, right? Square root of m minus 4. You could also say every ordered pair is going to look like that as well, because g of m and the square root of m minus 4 are equal, right? They represent the same stuff. Okay, so now that we got that out of the way, right? Talking about function notation, what does it mean? Hopefully it'll make a lot more sense as we go through. Got a bunch of examples here. Now I have two parts to example 1. First, I'm asked to evaluate g of 5, right? So remember, g of 5 means the value of function g. Right? The value of function g. So what's the output? Right? The output of function g when the input is 5. And remember that 5 is replacing m when the input is m equals 5. Right? So again, all I'm doing then, right, if I want to find g of 5, I just replace m with 5 everywhere. Right? So g of 5 is, and then, how do I calculate g of 5? How do I calculate the output when the input is 5? They're telling me how to do it over here. It's the square root of 5 minus 4, right? M is replaced by 5. And we simplify, right? This would be the principal square root of 1, which is just 1. So g of 5 is 1. Right? And that's it. That's all we're asked to do. Right? What's g of 5? It's 1. Now something else you could say then is that the ordered pair 5, comma 1 is in the function g, or would be on the graph of g if you were graphing g. Let me show you this. All right. Let me show you this. So I'm going to go to there's a free online graphing calculator called Desmos at desmos.com. And I'm going to enter the function as it was given to me, and that's the nice thing about Desmos. So you put g of m, right, the function notation equals, and then the other side has, how do I calculate the output when the input is m, right? The square root of m minus 4, and look at what shows up here, right? A graph, right? A graph. And remember what we said? We said g of 5 was 1, right? When the input was 5. Now remember, input is represented by the horizontal axis, right? Inputs represent, now usually we call them x and y, right? Usually the horizontal axis is x and the vertical axis is y. But the way the function's written here, the horizontal axis is now m, the m axis. And the vertical axis is g of m, right? The output, right? Or just g. And I'll draw this up on paper as well. But yeah, and let's look. We said g of 5 was 1, so input 5, output 1. And you see that point 5 comma 1 there on the graph? It's perfect, right? And that should be indicate no matter what I plug in for m, as long as it's 4 or greater, right? Because we're not taking square roots of negatives, right? These axes represent real numbers only, so shouldn't be taking square roots of negatives. Those are imaginary. Right? Yeah, but just know that you can graph these things. Right? There's inputs and outputs. You can graph them on the xy plane. It's just the axes might not be called x and y anymore, right? So let me do that here actually. So again, you got horizontal axis. Now remember, the horizontal axis will usually represent the inputs, which in this case are m's, right? So this is the m axis now. And the vertical axis, right? The vertical axis represents outputs, range values, which in this case are called g of m. So this will be called the g-axis for short, right? Or the g of m axis, but usually just for short, it's just the g-axis, right? That's the name of the function. Same thing. And again, if you want to replace m with x and g of m with y, you can. Right? So this is the same thing, right? This is the same as, I know this might be confusing with all the letters, but this is the same as y equals the square root of x minus 4. Right? Just replace m with x and g of m with y, and you get the same equation. It really is the same graph. Alright, so we said input 5, right, output 1. Alright, there's a point. Hopefully you see that if I plug in 4, I get 0. Alright, if I plugged in 8, I'd get 2. Alright, 6, 7, 8, because the square root of 4, 8 minus 4 is 4, square root of 4 is 2. And so on, and you get this, you saw the graph on Desmos, right? It looks something like this. It would go up forever that way. A very, very rough sketch. All right. Okay, just know that you can do this with all these functions. All right, so now, part 2 of this example 1, we're asked to solve an equation. Right here, when they said evaluate g of 5, I was given an input, right? M inside the parentheses there. The input was 5. They gave me an input. Here, remember, g of m is equal to the output. So here I'm given an output, 2. Right? The number 2 is an output. And I have to find the input. Right? Find input what inputs, what values of m give me an output of 2? Well, remember, g of m is equivalent to the square root of m minus 4. So this left side of the equation is the same thing as writing the square root of m minus 4. And we are being asked, when is that equal to 2? Right? And then we solve this it's a radical equation. So remember how to do that, right? The radical's isolated. I would square both sides. We'd have m minus 4 equals 2 squared is 4. Then I would add 4, get m equals 8. And there we go, right? And of course, check your solution, right? Don't make, square root of 8 minus 4 is the square root of 4, which is 2. You get 2 equals 2. This works. Right? Don't forget to check it. Yeah, so g of 8 equals 2. All right, replacing m with 8 gives me an output of 2. Also, you could say that the ordered pair 8, 2, right? Input 8, output g of 8, input 8, output 2 is in this function called g. And you go to our graph again, right? I'll show you, right? Here's 8, g of 8. And look at that. See, it's 8, 2. They put up the point. There's, well, let me label it. There's C, 8, 2. Right. Beautiful. Okay. So yeah, Desmo is very nice to help you visualize some of this stuff. All right. Wonderful. All right, so a lot of stuff there that's pretty cluttered. Just remember function notation here, right? If a is a function of b, you should be able to write b as an expression with a, f of a, and the name of the function. And then in parentheses is the variable for the input, right? The input variable. And then the entire thing is equal to the output. The entire thing, g of m, f of a, right, represents the output. And then the other side is also the output, but just how to calculate it, right, given a certain input. Cool, cool. All right, now in example 2, we're not given an equation. We're just given a table. We're just given a table. N with inputs n, and then output g of n. So again, we have the function called g. And if I were to graph, start making a graph here. Again, there's no equation here. They only gave me 5 ordered pairs here. There are 5 ordered pairs, 5 pairs, 5 pairings, whatever you want to say. Now the horizontal axis is going to be the n axis, right? The input axis. The vertical axis is the g axis, right? Or g of n, right? And again, you can replace n with x, and you can replace g of n with y if you want, and it's the same stuff. All right, so I've got input 1, output 8. Right, there's the ordered pair 1, 8. And 2, n is 2, g of n is 6, right? So n is 2, g of 2 would be 6. Right, so 2, 6, right? The ordered pair 2, 6 would be on the graph of this function. Input 3, output 7. Right, input 3, output 7. 3, 7. Right. Again, I'm just doing a rough sketch. If you want to put these ordered pairs on Desmos, now you can actually just put pairs on Desmos. You saw. Let's put these 5 points on there. Then we have input 4, output 6, so around here. And then input 5, output 8. Now don't connect the dots, right? They only gave us these 5 points, right? So don't connect the dots. As soon as you connect dots, you're graphing infinitely many points. So just those 5. So the first part, what's g of 3? So this means, n equals 3. So just what's the output when the input is 3? Well, that's here, right? Input 3, output 7. And that's it. G of 3 is 7. The end. And the ordered pair 3, 7 would be on the graph, and I already plotted that. Right? 3, 7. Evaluate G of 1, right? G of 1. Again, they gave me the input. Input 1. And then G of 1 is the output when the input is 1, which would be 8. That's it. Input 1, output 8. The ordered pair 1, 8 is on the graph, right? That's all they wanted, is what's the value of G at n equals 1. Right? What's the value of G with input 1? Just 8. All right, and then once again, in these first two parts, we were given the input 3, input 1. Here we don't know the input. The input is n, G of n. But G of n equals 6. So remember, G of n represents the output. So the output is 6. Output equals 6. So output equals 6. And again, this represents output 6. So when is G of n equal to 6? Well, there are two values that solve that. N equals 2 and n equals 4. Right? Or n equals 4. So the solutions to this equation, even though there is no real equation here, I mean, yeah, there is, but I don't have any expressions for the G of n. But we have n equals 2 or n equals 4. Both work, right? Both of these work because G of 2 equals 6, right? And we can check it, right? G of 2 equals 6, right? Input 2, output 6. We see that in our chart. See it in my graph, ordered pair 2, 6. Also, G of 4. G of 4 also equals 6, right? Input 4, output 6. And the ordered pair 4, 6 is on my graph. Right? So there's two solutions to that equation there in part C. Alright, so when there's a table with just a few ordered pairs like this, real easy to read, I'm hoping. Right? And again, I hope you understand what's an input, what's an output. Right? And it should make sense with the way function notation is written. Okay. Alright, next example. And I'm actually going to the book. Alright, like I said, all these I've either written them out or I'm just saying to myself, go to the book. So here I'm saying go to problem, try it problem number 8 from the text. Alright, so back on OpenStax here. You start scrolling to example 6, there's try it number 4, try it 5, right? I want to go down, I want to do try it problem number 8, right? I'm leaving the other ones for you guys. And using figure 4, which is this graph here, see figure 4, this parabola shaped graph, solve f of x equals 1. Alright, so I'll do my best to draw this picture. Now, remember, f of x equals 1. See, they don't give us the input. The input is x, right? Highlighted the whole thing. Sorry about that. Yeah. Alright, so the input is x. I do not know the input, but they tell us f of x. Alright, so this function's name is f, and f of x represents the output. They're saying the output equals 1, which would be the y coordinate, right? The vertical coordinate. So that's here on the y-axis, right? So you see that looks like at x equals 0 and at x equals 2 we get an output of 1. Alright, so once again I'll do my best to draw this and answer it on paper. So again, you can see why I said look at the book, because my hand drawing isn't that great. We have, horizontal axis is the input axis, right? The x-axis, the vertical axis, the output, and they labeled it, f of x. And they want us to, again, solve, f of x equals 1. And once again, this 1 is an output. it is on the vertical axis right here. So you could draw like a little horizontal line if you want, you know, at y equals 1, or the f of x equals 1 here, and see, you know, there's f of x equals 1, right? Y equals 1. And you see there are 2 points on the graph where y equals 1, or the output is, where the output is 1. And that's at 0 on the input axis and at 2, right? So the solutions to this equation, f of x equals 1, even though I don't know what the equation looks like exactly, I don't know what f of x represents, but the solutions I can clearly see from the graph are x equals 0, and the other one is x equals 2, right? Since, let's box these up, right? Since f of 0 would be 1, right? Input 0, output 1. Also, f of 2 equals 1, right? Input 2, output 1. So check on that. They both work. Wonderful, wonderful. Right. Very easy, especially when you're given a graph. You know, graphs, tables, pretty simple stuff in my opinion. You just have to understand what function notation means, right? You have to understand how to interpret it. What's in the parentheses is the input, and what the entire thing is equal to is the output, right? The entire notation represents the output. Okay. All right. Next question. All right, so again, we're given a function. This has a bunch of parts to it. So here we're given a function f of x equals, and then, you know, the input variable is x, the output f of x equals, and then over here they show you how to calculate the output, right, with this input x, right? So the expression over here, notice, involves only x's. All right, so evaluate the following, and I've done this already with the other examples. But, you know, what's the value of f when the input is -3? What's f of -3? So again, very simply, I'm just going through and replacing x with -3 everywhere. So using this side, right, using how do I calculate the output when x is -3? So it's -5 times, you know, x squared. So it's, you know, -3 squared. And I would get in the habit, if I were you, if there's stuff around it, to put whatever you replace in parentheses. Again, only if there's stuff around it, like powers and multipliers or minus signs, you know. Plus 2 times, and again, x is -3 here, then -1. And then we simplify, right? This is -5 times 9, right? Remember, you do powers first. -3 squared is +9. Then you start multiplying. 2 times -3 is -6, then -1. Then this is -45 minus 6 minus 1. That's, you know, -52. Right? -52, and that's it. All right, that's it. That's all they want. Right? Plug in your input and simplify. Now, let me show you that. All right, let me go again. I'll go to the Desmos website. I'll put in this function the way it was given to me. And we have f of x equals -5x squared plus 2x minus 1. And now again, the horizontal axis represents the input variable x. The vertical axis represents the value of f, or f of x. And I'll put in, you know, the point -3 comma, and then f of -3, which will be -52. All right, and I'll label it, and you'll see. All right, let me scroll way down here. All right, you'll see eventually that point will pop up. There it is. See, it's on this black graph. It's on the graph. I see -52 was the value of f at -3. Excellent. Okay, so back to the example. I'll keep that function up. We're still working with it. Part B, it's f of 2, or what's the output of f, or the value of f, when the input is x equals 2. Right, so I'm just, again, how do I calculate the output when the input is 2? So just go through and replace in this rule all the x's with 2. So that's negative 5 times 2 squared plus 2 times, instead of x, 2, and then minus 1. Alright, so this would be 4 times negative 5 would be negative 20 for the first term, plus 4 for the second term, 2 times 2, and then minus 1. So that's negative 17 all told, negative 21 plus 4. And that's all they wanted, right? What's the output when the input is 2? So the ordered pair, 2, negative 17, 2 comma negative 17 should be on the graph, and let's see that, right? So let me apply another point, 2 comma, and then again I can put negative 17, or I can just put, since I have function notation up there, f of f of 2, right? 2 f of 2, which will be at 2, negative 17, way back up here again, right? There it is, and let me label it, right? There it is, and see it's on the graph, right, on this black graph, 2, and then f of 2 is negative 17. Great. All right, now we get into some interesting stuff. In parts A and B, I just replaced x with a number. All right, I replaced x with a number. But you don't have to replace x with numbers. You don't have to replace, your input with a number. You can replace your input with an entirely different expression altogether. So that's what's happening in the last 3 parts. So here, in part C, we have, what's the value of f at negative a, or the opposite of a, right? That's a, another letter. But you do the same stuff. This function f is represented up here. And x is going to now be replaced by this expression negative a. So I just go through the rule, replace all the x's with negative a, and we simplify. So this is going to be negative 5 times, and then instead of x squared, now x is replaced by negative a. So negative a, to the second, plus 2 times negative a, right? X is replaced with negative a, and then minus 1, and then we simplify, and we get, negative 5. Now negative a to the second power would be positive a squared, right? And then 2 times negative a would be negative 2a, and then minus 1, and this is it, right? These don't go together, right? These are not like terms. So that's it. That's all. You're done. Now you could replace a with numbers if you wanted, right? Now, so watch this. What if a were 3? What if I replaced a with 3? Well, then you'd have f of negative 3. Right? What's inside the parentheses here is the opposite of my choice for a. Hopefully we get negative 52, because this is still the same function f. Right? This is still the same function f. So f of negative 3 should be, negative 52. And you can see that, I'll just say it out loud here. Replace a with 3. And this would be negative 5 times 9, negative 45, minus 2 times 3. Right? Replacing a with 3, negative 6 minus 1. It's the same thing up there. It's negative 52. Right. How about if a were 1? I can replace a with any letter, any number, just like I replaced x with any number. Well, if I replace a with 1, this would be f of negative 1. And 1's, a would be negative 5, and then minus 2, minus 1. This would be negative 8. Let's see that. Let's see if that's true. Is when the input's negative 1 for this function, is the output negative 8? Let's see. So So back on the graph of function f, input -1, output f of -1, and label it. And you see there's -1, -8. Fantastic. Alright, now I could also do this, right? I could do this here. We have our original function written out, right? And I could put in, -a, right? Where our input's -a, and the output is f of -a. And then you see it says add slider for a. And let me label this point. See, so when a is 1, you get input -1, output -8. When a is, 3, we saw that it was, input -3, output -52. There it is. And when the input was, let me just change this a bit. There you go, -10 to 10. And then just to change it by ones, have a step be 1. When the input's, 2, it'd be the order pair, -2, -25. When the input's 0, 0, it'd be a 0, -1, 0, -1 up there. Right? And so on. And I can play this, and just changing the value of a moves this point around. Right? Here it comes again. Okay. Yeah. But yeah, so we can do this with our variables, our variable inputs. But I replaced x with -a here, right? And then the output would be f of -a. Okay. So back, still working with the same function. All right, so this one's a little different, part D. See, this is outside the function, this negative sign. Here it was inside. It changed the input. And remember, inside the parentheses is the input. This negative outside, this is like having -1 times f of a. This is going to change the output. All right. So this is, negative f of a. Right, so anything outside just kind of stays outside. And then f of a, well, that's just take f, replace x with a. So it'd be -5 times, and then instead of x squared, a squared. Plus 2 times, and instead of x, replace it with a, and then -1. But what we're doing here is we're taking the opposite of this. Right? We're taking the opposite of this. So just distribute the negative here. The opposite of all this would be positive 5a squared minus 2a, and then plus 1. But notice this is just, this is the opposite of f of a. -1 times f of a. So this is actually not going to give us points on the graph. It's going to give us points on the opposite of this graph. Right. Let me show you. So if I put in, y equals the opposite of f of x. So you put the -1 outside. That just, now we'll talk about this in further detail in a future video, but taking a function and just multiplying it on, by -1 gives you a graph that's a reflection across the x-axis, a vertical reflection. So see, all the outputs up here are the opposite of the outputs down here. So the black graph's outputs are and the red graph's outputs are opposites. Right. So if I plot these points, get rid of these here, and I plot the point, A input was A, right? The input X was replaced by A, but then we had the output of, the opposite of f of A. And I'll do the same thing where we add the slider for A. And now you see it's on this red graph and not the black graph because we're on the opposite of the f of A, right? Anything done outside changes the function entirely. But like I said, we'll go into that in much more detail in a later video on transformations of functions. Okay. All right. So, and then back on paper here. All right. So like, see how if A were 1, this value here would be 5 minus 2 plus 4. That'd be 4. Right. So I would plot the ordered pair 1, 4 would plot here. Right, see when A equals 1, I'll label this. See the ordered pair 1, 4 on the red graph, not the black, not the original black graph. It's the opposite, right? So just be careful. Okay, and then finally, right now, so I'm still keeping the original function now. Right, going back to the original function. Look at part E. Let me separate these. Now part E, notice, in parts C and D, I replaced X with an expression that had just one variable A in it, right? In part E, I'm replacing X with an expression with 2 letters, A and H. Still no different. Still no different here. Watch this. So the input now is this quantity A plus H, right? This is the input now. This A plus H quantity replaces all the X's again. X is replaced by A plus H. So this would be -5 times, and then instead of X to the second power, now it's this the quantity A plus H to the second power. And then you have plus 2 times, and then again, instead of X, it is now this quantity, right, put in parentheses, A plus H. And then you have, -1, so that's not changing, right? -1. Alright, now we simplify this. Right, so I'm going to pull up a new piece of paper. I'm running out of room here. Now remember, when you square something, that means you multiply it by itself. So you take A plus H times A plus H again, and then do foiling and combining like terms. Don't just you can't distribute powers over sums. This A plus H to the second power, it's not A squared plus A squared. Please know this, right? I'll write this over here. A plus H to the second power is not equal to A squared plus H squared. Right, don't just write that. So we have -5 times, and then when you square this, it'd be A squared plus 2AH, right? You'd have A times H twice, and then plus H squared, right? So it's almost that, but you have this middle term of 2AH. Then here I'm distributing the 2. We have plus 2A plus 2H, and then you have -1 still. And then after distributing the -5, you have the following. -5A squared minus 10 A times H, and then -5 H squared, and then plus 2A plus 2H minus 1. And none of these terms go together. None of these terms are like, don't have the same variables to the same powers, right? So that's it. Alright, so look at what happens here. Alright, this still is representing the same function f. So inputs, inputs and outputs should be the same. Right? It's still this same function f. It's not the opposite of f like part D was. It is still function f. And watch, let me replace, like I was replacing in parts C and D, I was replacing A with some letters. Well, here let me replace A and H. I'm going to replace both of them with some numbers. Right. So how about if, if A was 1 and H was 1. if I replace both of these, a and h, with 1, then you'd have the following. F of 1 plus 1, a plus h, 1 plus 1, f of 2 would be equal to, and then again, just replace all the a's and h's with 1 here. You'd get negative 5 minus 10 would be negative 15, minus 5 would be negative 20, plus 2 would be negative 18, plus 2 again would be negative 16, minus 1 would be negative 17. Alright. You'd have f of 2, if you replaced a and h with 1, both of them with 1, you'd have f of 2 equals negative 17. And let's see that. Wait, watch this. Alright, so I'm going to go back. Again, same function up there, that same function I was given, function f here. But now I'm going to go f of a plus h, and it's going to ask me to add sliders for both of them. Right? And I'll say, well, actually, let me plot the ordered pairs, sorry. So input a plus h, comma, output f of a plus h. All right, and then add sliders for both a and h. And you see when, and I'll label this point, and you see when a is 1 and h is 1, right, you get 2, negative 17. Right, there it is. Right. And going back to the paper, now you're probably asking, why the heck are we doing this? You know, why not just keep it as x? Why replace it with these other expressions? Well, there's a reason, all right, and you'll see the reason for this kind of stuff in a calculus course, Calculus 1. So that's beyond the scope of what I'm going to talk about here. But here's another one. Like, let's say if a were, 0 and h were, negative 3. If a were 0 and h were negative 3, then you'd have, f of 0 plus negative 3. That'd be f of negative 3. Well, we saw that earlier as well. That was negative 52. Right, and you can try it. Replace all the a's with zeros. Well, then this term would be gone, this term would be gone, this term would be gone, and h with negative 3, and you'd have, negative 45 here, minus 6 here, minus 1, that'd be negative 52. And you get the point negative 3, negative 52. Well, let's see that, right? If I replace a with 0, right, and h with negative 3, the point being labeled here, this a plus h, comma, f of a plus h, should be the point, negative 3, comma, negative 52, right, which we saw earlier. And you could, there it is, right? And you can replace, again, you can replace a and h with any numbers you wish. Just kind of move these sliders around, and it'll move the point around. In fact, I can play both of these, and you see how the point moves around this graph. I mean, it's kind of moving pretty rapidly, but here it comes. Yeah, it's too fast. I can probably slow these down a bit, but I'm not going to. All right. So, see, here when a is negative 4.08 and h is negative 2.33, right, we're getting. Let's see, where is that point? There it is down here, negative 6.41, 219.261. All right. Yeah. But yeah. So again, same thing. Just pay attention to what's inside the parentheses, right? That's your input. And then what is the function notation equal to? Right? That's your output, how to calculate the output. All right. So that was example 4. And then I've got some very similar stuff, for the next couple examples here. Right. So example 5. Again, we're given a new function. Again, it's still called f, right? But it's a new f, right? A totally new page. F of x equals, and then again on the other side is the output as well, right? They both represent the output, but over here is how you calculate it, and the input is x, right? The input variable is x. All right, so what's same stuff? It's the same 5 things, right? But obviously we'll get different results because this is definitely a different rule than the last one. All right, so what's f of negative 3? So my input is negative 3. So I'm just going through this rule here, and we take 6 times negative 3 minus 1 in the numerator, divided by, and then 5 times negative 3 plus 2 in the denominator, just replacing all the x's with negative 3. Alright, so the numerator is negative 19, right? Negative 18 minus 1. The denominator is negative 15 plus 2, be negative 13, and a negative divided by a negative is a positive, right? Positive 19/13. Alright, so between 1 and 2. Alright, that's somewhere between 1 and 2. But 19/13, right? One point something. If you want to put that in a calculator, you can. But let me go back to the Desmos site. I'm going to put this function in. Right? We have f of x. It was f of x. F of x equals, and the numerator has 6x minus 1. Notice I put that in parentheses because it has multiple terms. Denominator 5x plus 2, and then I guess once it's all entered, if you don't like having the parentheses, you can get rid of them. Right. And yeah, let me put in, our input was negative 3, and then output f of negative 3, and you're seeing, now they round it to 3 decimal places, 1.462, right? I said it was between 1 and 2. That's 19/13, right? You can actually do calculations here too, right? 19 divided by 13, 1.461, blah, 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 rounded to 1.462. Okay. Cool. All right, so far, and look at it, it's on the blue graph. It's on the graph of our function, this blue graph here, great. If it was off the graph, then I'd be like, oh, I did something wrong, right? Or either I typed something wrong or I miscalculated, whatever. Alright, so back to it. So part B, what's f of 2? What's the output of this function when the input is 2? Again, just going through and replacing the x's with 2. So the numerator is 6 times 2 minus 1. The denominator is 5 times 2 plus 2. Alright, so the numerator is 12 minus 1, it's 11. Denominator is 10 plus 2, that's 12, 11/12. Right, and again, that's that's between 0 and 1, right? 0 point something. You want to enter it into a calculator and round it, you can. And let's see. Right, let's check it. Go back to our Desmos site here. Right, so this time I'm going to enter the point. Our input was 2, and then f of 2 for the output, and there it is. Right, let's label this and see the output here is 0.917. That should be what 11/12 is rounded to 3 decimal places. All right, see it's 0.9166666. It's 0.917. Okay, great. All right, and then back to this. All right, then in part C, notice we're not changing the function itself, right? It's still function f. It's not the opposite of f, like in D, right? Something done to the outside actually changes the function itself. But it's still function f. We're changing the inputs though, right? The input now is negative a, right? The opposite of a. So once again, I go through and replace all the x's with negative a. So it's 6 times, negative a minus 1 divided by 5 times negative a plus 2. And this will be, negative 6a minus 1 in the numerator and negative 5a plus 2 in the denominator. And this is great. Now, if you don't like having a negative lead coefficient in your denominators, which I personally don't, you can multiply the numerator and denominator by negative 1, and that'll give the numerator 6a plus 1, and the denominator 5a minus 2, right? Just taking the opposite of the numerator and the opposite of the denominator. All right. So I like this personally, because the lead coefficient in the denominator is not negative, but whatever. They're both the same. All right, and now, again, just a little test here. If a were 0, you'd have f of 0, right? The opposite of 0 is 0 still, equals, and then, 1 over negative 2, negative 1/2. So if I replace a with 0, right, you'd have an output of negative 1/2, the point that should correspond to this should correspond to the point 0, negative 1/2. You know, if a were 1, then you'd have f of negative 1, right, replacing a with 1, that puts negative 1 as the input, equals 7 thirds. Right, 7 thirds, 2 and a third. Let's just see that happening. Right, let's see that happening. So going back here, right, keeping the original function up, and now my points I want to apply are, you know, input negative a, output f of negative a, and I'll add a slider for a. And again, when a is 1, right, remember the output should be 7 thirds, right? That's 2.33333, right? There it is. When a was 0, I said it should be at negative half, right? Negative half for the output, 0.0 negative half. And when a is 2, right? When a is 2, you know, the input will be negative 2, and output will be f of negative 2, right? Which would be 1.625. Looks like 1 3/8. Okay. Great. Yeah, and again, you just play around, move the value, change the value of a, that'll move this point around. Great, but it's all on this function f here. All right. Now the next one actually changes the function a little bit, right? It's on, you know, just like in part D of number 4, right? For number 5 here, same thing. I've got, you know, this negative on the outside changes it. You know, it's not just function f now. Now it's the opposite of function f, and function f has the input of a. Right? So this is the opposite of, and then f of a, I just replace x with a. So you have 6a minus 1 in the numerator, 5a plus 2 in the denominator. And you don't multiply both the numerator and denominator by negative 1, right? This is negative 1 over 1. You multiply the numerator, negative 1 and that. You multiply, you know, this is like negative 1 over 1, right? You multiply the numerator by negative 1 and the denominator by 1. So that'd be it. Or the denominator by negative 1 and the numerator by positive 1. It doesn't matter. Right? But you can't do both. So it'd be negative 6a plus 1 in the numerator, and then still 5a plus 2 in the denominator. Okay. And that's all they want right there. Now again, plugging in values of a here will correspond to points on the graph of the opposite of f, a new function, right? So back on the Desmos site, you know, if I put in y equals the opposite of f of x, look at that graph, right? See, it's, now let me change the color so it's a little more contrasting. Make it red or something, right? And you see this red graph and blue graph, right? Every point on the blue graph has the opposite output of points on the red graph, right? And once again, I'll say it later in a more detailed video on transformations, but taking a function and just multiplying it by negative 1 like this reflects it across the x-axis. Right? So the red graph is just the blue graph reflected across the horizontal axis, the x-axis. All right, and now look, see if I put in, see, input a, right? The input for the function was still a, right? It was f of a, but then the output was the opposite of f of a. And then I add a slider and we'll plot this point. Right, and you see how it's on the red graph and not the blue graph? Right, it's on the graph of the opposite of f. And moving this around just moves the point around the red graph, right? Okay. Great. All right, and then finally, for this example, just like in number 4, part E, number 5, part E is, you know, the function f again, right? So not the opposite of f, but just f again. So we'd be on that blue graph, the original graph, of a plus h. So again, the input is the quantity a plus h. I go through and replace all the x's with the quantity a plus h. So the numerator is 6 times the quantity a plus h minus 1. and the denominator is 5 times the quantity a plus h plus 2. And distributing the 6, distributing the 5, we'd have 6a plus 6h minus 1 in the numerator, and 5a plus 5h plus 2 in the denominator, and that's it. No other way of simplifying this. Alright, and then once again, you can replace both a and h with some numbers, and it'll tell you points on the graph of f. So how about if a were, I'll just do a and h are both 1 again. If a was 1 and h was 1, you'd have f of 2. Now we've already seen f of 2. It should be 11/12 from part B. See, 1 plus 1? Well, let's see, it would be 6 plus 6 minus 1. That's 11. 5 plus 5 plus 2, that's 12. 11/12. Right. And again, you can replace a and h with really any numbers you want, as long as the denominator is not going to be 0. And it should end up revealing a point on the graph of f. Right? I'll show you that. I'll show that to you one more time. So input, right, same functions up there, right? Input a plus h, comma, output f of a plus h. And I'll add sliders for a and h. And you see when a is 1 and h is 1, you get that point 2, comma, 11/12, right? That was the 0.916666666, 0.917. And when they're both 0, you should get -1/2 as the output, right? And it should give you f of 0. 0, -1/2. Look at that. And when a is, here's the thing though, when a is when a and h are opposites, when a is -1 and h is +1, look at this. It goes back to f of 0, right? Because a plus h will be 0. Right? So yeah, just move the values of a and h around, play with them, and you'll move to different points on this blue graph, right? Great. All right, so that's it for that function. That's it for that example. All right, so I'm done with stuff like, well, not exactly done with stuff like that, but like not so many parts anymore this time. All right. So number 6. We're given a function with function notation, right? G of x, a function called g, inputs x, the output's g of x, and then over here is how to calculate the output. You take 5 minus x squared. Now we're asked to evaluate the following expression. Now notice there's a couple instances of g in this expression. We have, g at x plus h minus g at x, which is already given to us, and then all that in the numerator, and then h in the denominator, obviously with h not 0, right? You can't have 0 in the denominator. Now this expression here has a fancy name that's going to be monumentally important to you in a calculus course. This is actually referred to as the difference quotient of function g. All right, if I had a function called f of x plus h minus f of x divided by h would be called the difference quotient of f. All right. It's a change in outputs divided by a change in inputs. It's actually a slope. All right, but again, I'm not going to get into all this. All right, we're not going to talk about difference quotient in too much detail here. I just want to point it out that you will, especially if you move on to a pre-calculus and calculus course, this will come up quite often in those courses. But for right now, we're just simply inputting things and simplifying expressions. All right, so g of I'll do this one at a time. We have g of x plus h. I'll do this off to the side. G of x plus h. So now my input, right, instead of being x, is x, this quantity x plus h. It's kind of like a plus h in numbers 4 and 5. So I just go through the rule for g and replace all the x's with x plus h. So you have 5 minus, And then instead of just x squared, now we have this quantity x plus h squared. And I'll simplify this, right? This is 5 minus, and don't forget to, you do powers first before multiplication. This is like -1 times this. You square the thing first. X plus h squared would be x squared, plus 2 times xh, right? You'd have x times h twice. And then plus h squared. And then you distribute the negative, and we'd have 5 minus x squared minus 2xh minus h squared. Right, so that's going to replace this part of the expression. And we already have g of x, right? G of x is already given to us. It's 5 minus x squared, simple enough. So now I do my replacements. Right, so this expression we're asked to, this difference quotient of g, this expression we're asked to simplify. I'm going to replace g of x plus h with this quantity. Right, so we have 5 minus x squared minus 2xh minus h squared. Right? That is g of x plus h. Then we have minus, and now I'm replacing, and again, when you replace something in an expression, usually you put parentheses around it, right? Especially if there's a minus or something else around it, right? So g of x is this quantity, right? The quantity 5 minus x squared. And then, that's all in the numerator. And then we have just simply h in the denominator. And we are asked to, simplify this, which you'll see will be able to be done after I distribute this negative. Right, and we have, now we don't need parentheses around this. There's nothing multiplied by it. It's not being raised to any powers. Right? So we have 5 minus x squared minus 2xh minus h squared in the numerator, and then minus 5 plus x squared, right, after subtracting the g of x. And then all this divided by h. And then something nice happens here in this difference quotient, or at least it should with a polynomial anyway. See, I have 5 here minus 5 there. Those are gone. Negative x squared here plus x squared there. Those are gone. So all I'm left with in the numerator are terms that have h. You'd have negative 2xh minus h squared. And then this is divided by h, and then if you actually go through and divide each term by h, negative 2xh divided by h would be negative 2x. And then negative h squared divided by h would be negative h. Or you could factor h out of the numerator and cancel the h's, but you'd be left with this thing here. Right? Negative 2x minus h as your final result, right? Yeah, after you're asked to simplify this fraction. All right, now again, what does this mean? This actually represents a slope of what's called a secant line. And again, I'm not getting into all that. All right, now I'll mention difference quotient. You can look it up if you want to read more about it. It'll be obvious. It'll definitely be mentioned in a future video, or in a pre-calc video, or a calculus video, but not right now. All right. Next page. I'm just working with function notation some more. I have a function called k. The input is now t, right, equals 2t minus 1. Here's how you calculate the output. Right, the output is k of t. So again, if I wanted to graph this thing, and I could go to a calculator, but the input variable is t, so the horizontal axis is the t-axis. And the output variable, or the output's called k, or k of t. You can just call that the k-axis if you want, or k of t. And the first one's simple enough. They give us an input. All right, the input is 2. What's the output? What's k of 2? All right, k of 2 is 2 times, and I'm replacing t with 2, right? 2 times 2 minus 1, that's 4, minus 1, that's 3. So that's all they want, right? And if I were putting this stuff on the graph, input 2 for t, and then k of 2 is 3, right? Input 2, output 3. And there's an ordered pair on the graph, right? There's a point on the graph of this function k. And you can plug in some other stuff, right? You know, if the input were 0, the output would be -1, right? K of 0 would be -1. Hope that's obvious. And another thing I'm hoping you notice is that this is a linear polynomial here. This is a linear function. It's just like y equals 2x minus 1, right? If you replace t with x and k of t with y. So the graph of this thing should look like this. All right, there's the graph of this function called k. All right. Great. All right, now, part B, you know, they don't give us the input. They give us the output and want us to find the input, solve for t. Right? So again, this is the output of 7. Right, so if I went to the graph here, you know, output of 7, let's say 7's up here on the output axis, right? Here's where k of t equals 7. Right, k of t equals 7, y equals 7. And so we're looking for what's this value here? All right, question mark. What's this input that gives me an output of 7? All right, well, k of t, well, I already got, you know, k of t is the output, and that's equivalent to 2t minus 1. So this left side of the equation is 2t minus 1, and the right side of the equation is still 7. And then I solve this, right? I would add 1, divide by 2, t equals 4, right? And then check it, right? Don't forget to check your solutions. 2 times 4 is 8, minus 1 is 7, that works. So that's it. That's the only solution. All right, so back on the graph here, this question mark is the number 4, right? Input 4 gives me an output of 7, right? And again, it's just a linear equation, so I'm not going to go to the Desmos site for that one. Great. All right, example 8, very similar to example 7. Again, we're given a function. Now this function is called p. The input is c, and the output is p of c. And so is this, right? They're equal. So here's how you calculate the output, right? C squared plus c. All right, so evaluate p of -3. All right, so just replace c with -3. So instead of c squared, it's, you know, -3 squared plus, and then instead of c, right, -3. So this is just 9 minus 3. This is 6. Right. And again, if you were to graph this function, the horizontal axis would be the c axis, the vertical axis would be the p axis, right, or p of c. And input -3, output 6. Right, this point should be on this graph. All right, now this is not a linear function. All right, it's a quadratic polynomial. Right? You might have seen graphs of these as parabolas. Right? I'll actually put this one in. P of c, right, equals c squared plus c. Right? And again, you should see the ordered pair. You know, -3 comma p of -3 is at 6. Right? Let me label it. P of -3 you see is 6. All right, now in part B, we're not given the input, right? We don't know what C is, but we know what P of C is, right? We know what, again, we know what the output is. All right, so once again, you know, P of C we know is C squared plus C. Right? So this left side of the equation is C squared plus C. Right side is just the number 2. Right? And I'm solving this quadratic equation. Now you can solve it by completing the square. You can get everything to one side and use the quadratic formula, or try factoring, right? I'm going to get everything to one side here. C squared plus C minus 2 equals 0. And again, you can use the quadratic formula here now. if you remember, or factoring. This actually factors nicely. This is c plus 2 times c minus 1. And the only way a product is equal to 0 is if one of the factors is 0. So c is either negative 2, that would make the first factor 0, or positive 1. And there's your solutions. Right? Check them. Right? Negative 2, positive 1, they work, right? 4 minus 2 is 2, great, and 1 plus 1 is 2, also good. Right? I checked them both mentally. And back on the graph, right? Back on the graph, if I put in the horizontal line y equals 2, I'll make this like a dotted line, right? Because I'm trying to figure out where the output is 2. Where is the output 2? Actually, I should probably make it solid, because then they'll point out where they intersect. Let me do that. Make it solid again. All right. And see that they point out where the graph of y equals 2, if I click on y equals 2, they point out where they intersect the black graph. See, at 1, 2, and negative 2, 2. And we said earlier, right, the solutions were c equals negative 2 and c equals 1. Right. So you can see the solutions from the graph there. Wonderful. All right, and that's all I need for this function. All right, example 9. Another function notation here. This function is called f. All right, the input is x. The output is f of x, which is also, the square root of x plus 2, right? How you calculate the output. All right, so what's f of 7? Well, that'd be the square root, the principal, the positive, non-negative square root of 7 plus 2, which is the square root of 9. And, again, the principal, the non-negative square root of 9 is 3. All right, so if I were graphing this, the ordered pair 7, 3, all right, 7, 3 would be on the graph. I'm not going to show you that one this time. All right, you can do that on Desmos on your own. All right, and then part B, solve this equation here, right? Find the inputs that give you an output of 4 in this function. Well, f of x is equivalent to the expression, the square root of x plus 2. So on the left side here, I have the square root of x plus 2. On the right side, it's still the number 4. Square both sides. You got x plus 2 must be equal to 16 then, right? 4 squared. Subtract 2, x equals 14. Right, that's it. Right, f of 14. Right, f of 14 should be equal to 4. Or you could say the ordered pair 14, 4 is on f, right, is on the graph of this function f. All those mean the same thing. Wonderful. All right, so my next examples, I'm going to go back to the text. Right, I just have the exercise numbers written out because I think they're graphs. And let's take a look at them. All right, so example 10, saying let's do exercise 52 from the text. All right, so going back to the OpenStax text here. Let's go all the way down to the exercises at the bottom of the section. And I want to do exercise 52 that relates to this particular objective. Alright, so given the following graph, this graph here, this little arch here going up forever with the little arrow, right? Evaluate f of negative 1. So remember that input is negative 1. And from the look of this, when the x coordinate is negative 1, the output, f of x, the output, the y coordinate, looks like positive 1. So f of negative 1 is positive 1. And I'll write all this out in a second. And then here, again, we don't know the input. Right? We don't know x. We know the output is 3. So go to y equals 3, and then, what's this point here? looks like 6. It looks like 6 would give me an input of 6 would give me an output of 3. Right, so again, I'll roughly draw this up. And a very, very, very rough sketch of this. Again, this is a graph of, y equals f of x. We don't know what exactly the rule for this is. And yeah, so f of -1, and you go to x coordinate -1, output is 1, positive 1, right? So that was part A. F of -1 is positive 1. And then f of x, when's that equal to 3? Well, that happens when, looks like, y equals 3, the output is 3 when x equals 6. Right, so the solution there was x equals 6. Right. Okay, for part B. Alright, so that was all for exercise 52. Alright, then number 11, exercise 54, very similar. Another graph, and they ask us some information. So again, I'll leave the odd numbered ones. You can actually look at the solutions by clicking on the highlights, the links. So I'll leave those to you if you want to work on those. So given the following graph, again, this kind of this V-shaped graph down here. Right. So first, what's f of 4? Right, so input 4. What's the output? Looks like -3, right? Go to 4 on the x-axis. Looks like we're getting -3 on the y-axis for the point on the graph. So f of 4 seems to be -3. And then when is f of x equal to 1? When's the output 1? Well, it looks like that's at 2 places. See, when the y is 1, you got this point here and this point here with a y value of 1. This point has an x value of 0. So that's one solution, 0 for x, and this other one looks like at -6. All right. So again, I'll just make a rough drawing of this and answer this stuff on paper. So again, a very, very rough sketch of this. Again, this is the graph of y equals, f of x. They don't tell us what the rule for f of x is. Part A, what was f of 4? Right, and it was 2, 3, 4, and then it was down to like -3 or something. I didn't plot that point, but there it was. It was equal to -3, right? When the input was 4, the output was -3. Right. And then part B was when was f of x equal to 1, and that happens at 2 places, right? That's the output is 1 when x is 0 and when x is -6. So when x equals 0 or, when x equals -6. I'm not saying and because you can't have x be both at the same time, right? So 2 solutions for that one. Great. And example 12. Another exercise from the text, exercise 66. Let's take a look at that. So 66, probably another graph. Right? Oh, it's a table. So yeah, for the following exercises, use the function f represented in the table below. So they don't give us a graph, but they give us a table with like 10 ordered pairs on this graph, right? There's 10 columns here. So you have inputs on the top row, x, and then outputs, f of x on the bottom row. Right? And 66 is just simply, what's f of 3? Input 3, output 53. Now if you were doing 67, when's f of x equal to 1? Well, look at where's the output 1? That's when x equals 2. Right? So the solution to this equation is x equals 2. But 66, we're just asked, what's f of 3? It is 53, right? I'm not even going to write that out, the table anyway. We just have f of 3 equals 53, right? And that was it. I'll just circle it real quick. Right? Very, very simple stuff. Okay, moving on. the last several examples you've seen kind of already. It's very, very easy. Just here's a function called f. The input is x, and then f of x is the output, and over here is how to calculate the output, right? They both represent the output. And yeah, so what's f at negative 2? So that'd be 4 minus 2 times negative 2, right? Just replace x with negative 2. This would be 4 plus 4, that's 8. Right. So input negative 2, output 8, right? The ordered pair negative 2, 8 would be on the graph of f. Right? Now I'm only going to write that for this first one. You should be able to tell other points on the graph of this function the rest of the time. Part B, what's f of negative 1? Right, so again, input negative 1. So it'll be 4 minus 2 times negative 1, or 4 plus 2, which is 6. So input negative 1, output 6. The ordered pair, negative 1, 6, would be on the graph of this function. What's f of 0? It would be 4 minus 2 times 0, or just 4. So input 0, output 4. Right? Ordered pair 0, 4. F of 1 would be 4 minus 2 times 1. It's just 4 minus 2, which would be 2. Input 1, output 2. Right? The ordered pair 1, 2 would be on the graph. And input 2, what's f of 2? Would be 4 minus 2 times 2. That's 4 minus 4. That's 0. So input 2, output 0. The ordered pair 2, 0 would be on the graph. Again, you can go to Desmos, draw it by hand, see all these ordered pairs showing up, but I'll leave that to you. I got another example. Again, very simple stuff, all the same thing here, just a different function. So here f of x is 8x squared minus 7x plus 3, and I'm doing the same 5 values, same 5 inputs as example 13. So here, what's f of negative 2? The value of f at negative 2, the output when the input is negative 2. Right? So this would be 8 times negative 2 squared minus 7 times negative 2 plus 3. Now negative 2 squared is positive 4 times 8 would be 32, and then negative 7 times negative 2 is positive 14, and then plus 3. So that's 46 plus 3, that's 49. Let's stop circling in different colors, just circle it in black. Right? So input negative 2, output 49. And again, you can double check that by checking a graph or whatever. But you should be verifying your answers in some way. F of negative 1, input negative 1. You have 8 times negative 1 squared minus 7 times negative 1 plus 3. So this would be 8 times 1, 8 plus 7, right, negative times negative, and then plus 3. So this is 18, 10 plus 8, 18. Input negative 1, output 18. Wonderful. F of 0 is easy, right? Just be 3. I'm just gonna, there's not a lot of room over there, I'm sorry, but any term with x in it would just disappear. Right? 8 times 0, 7 times 0. So 0 minus 0 plus 3 is just 3. Right? F of 1, 8 times 1 squared minus 7 times 1 plus 3. So this would just be 8 minus 7, which is 1, plus 3 would be 4. So input 1, output 4. And then finally here, for this problem, 8 times 2 squared minus 7 times 2 plus 3. So that's 8 times 4, that's 32, minus 14, then plus 3. That'd be basically 32, and then minus 11 would be 21. Right? 21, or 18 plus 3, 21, either way. Right, so input 2, output 21. And again, I leave it to you to verify that all 5 of these points, these are all 5 input-output ordered pairs, are on the graph of this this function. All right. Example 15, same 5 inputs, just a different function again, just to keep practicing. Right? So first one, I'm inputting -2. Right? So numerator, you have -2 minus 2. Denominator, -2 plus 3. So the numerator is -4. Denominator is 1. And that's just -4 then. Right? Input -2. Output -4. F of -1 numerator would be -1 minus 2. Denominator, -1 plus 3. So the numerator would be -3. The denominator would be +2, and that doesn't simplify, right? -3 halves, -1.5. Great. F of 0, input 0 for x. So numerator is 0 minus 2. Denominator is 0 plus 3. So that's just -2 in the numerator, 3 in the denominator, and there's your output, -2/3, right? 0 input, -2/3 output. F of 1, 1 minus 2 in the numerator, 1 plus 3 in the denominator. So it's -1 in the numerator, +4 in the denominator, so the output's -1/4, or -0.25 if you wrote a decimal. So input 1, output -1/4. And finally, for this example, f of 2, 2 minus 2 in the numerator, 2 plus 3 in the denominator. That's 0 in the numerator divided by 5 in the denominator, and 0 divided by any non-zero number is just 0. Alright, so input 2, output 0. Great. And of course you could put in any other numbers you want. It doesn't have to be these 5 all the time, -2, -1, 0, 1, and 2. Just make sure you're not dividing by 0 ever and taking square roots or even roots of negative numbers. And we'll add to that list of restrictions later too as well. And I've got one final example involving this function notation, evaluating a function or functions. So I've got 3 functions listed here, but we're only going to need 2 of them. Alright, we have f of x is 3x minus 2. Function g of x is 5 minus x squared, and function h of x is -2x squared plus 3x minus 1. And we're asked to simplify, evaluate the following expression. We have 3 times f of 1 minus 4 times g of -2. So f of 1, remember, that's the output of f when the input is 1. So let's find that off to the side here. F of 1. Now pay attention though, right? Don't go to all 3 of them, right? This is just function f. F of 1 is 3 times 1 minus 2. Right? Replace x with 1. That's 3 minus 2. That's just 1. So this is 3 times, and then f of 1 is just 1. So that first term there is just 3 times 1. Then we have minus 4 times, and then I'm doing g of -2 next. Again, I'll do this off to the side. G of -2. So again, I'm going to function g. Pay attention. Not f, right? Not h, but g. G of -2 is 5 minus, and then instead of x squared, right, -2 squared. Well, that's just 5 minus 4. -2 squared is +4. That's also 1. So I'm replacing g of -2 with a 1. And 3 times 1 is 3, minus 4 times 1 is 4, and then 3 minus 4 is -1, right? The final value of this expression is -1. Okay. Now this wouldn't really correspond to any particular function at all, but it's just another way, just another problem where you're practicing plugging in values to a function and getting outputs and using them to simplify numerical expressions. Right? There's really no graph here for 3f and 4g. You could make a graph of 3 times f minus 4 times g, but I wouldn't want to input 2 totally different numbers to a function. Right? Okay. So that was a bit, all right, about an hour and a half there. But lots of examples, lots of practice here. using function notation, evaluating functions with numbers as inputs, with variable expressions, as inputs like a plus h or x plus h, like I had earlier. Alright, so I'm hoping that watching me go through these 16 examples here helps you in some way when you're asked to evaluate functions, use function notation on your own. And thank you very much for watching.